Okay, so last Tuesday we discussed the weak law of large numbers as well as the central limit theorem. So in section 8.4, we will discuss the strong law of large numbers. Right, so now I will state the strong law of large numbers in theorem 8.4.1. Okay, so let x1, x2, be a sequence of independent and identically distributed random variables, each having finite mean. Equal to mean. Okay. Right, so we would require that x sub i's are independent and identically distributed and have a finite expectation. Okay. Then, with probability 1, the sample mean, all right, so this is the sample mean up to the nth term, converge to the mean as n goes to infinity. Okay, i.e., there exists an event omega 0 in the sigma field or sigma algebra F with probability equal to 1, such that the limit of the sample mean at the outcome omega, okay, is equal to mu for all outcome in the event omega 0. Okay. So with probability 1, okay, for every omega, or every outcome omega in this event, okay, the numerical sequence, because for each outcome this is a constant, right? This is a real number, and so that this is become to a sequence of real numbers. Okay, and then as n goes to infinity, this is sequence of real numbers converge to the common expectation mu here. Okay. Right. Right, so in today's class lecture, we will not give a complete proof. So, but if you want to have a complete proof of theorem, of this theorem, right, you can refer to a theorem in Kadai-Chung's textbook. Okay. Right now in today's class lecture, we will provide a proof if each x of I have, so x of i's have finite force moment for central moment, we see. Okay, so this condition is stronger than the condition needed here, because in the statement of this stronger or large numbers, is required to have a finite expectation, which means the finite first moment. Okay. Okay, so proof. Okay. First, assume that the mean of x of i's it's 0. Okay, and then we let the partial sum of xi to be x sub n. So x sub n is the sum of the first n terms in the infinite sequence. And consider, so we consider that the first moment of this partial sum so we write the first moment will be the square of the partial sum. Okay, and so we can compare it. And the square of the partial sum consisted of the sum of square of xi plus 2 times that okay. So these two terms in the parentheses is equal to the square of the partial sum, and then we take the square here. Okay, and so that we can write down. So this is the expectation of summation I from 1 to n xi, the fourth power, plus 2 summation 1 less than I xj less than n xi square times xj square plus 4 summation I from 1 to n summation j less than k less than n xi square xj and xk. Okay. Plus 4 summation xi, xj, xk, and xl. Okay, so that the further squaring give us these 4 sums here. Okay, give you these 4 sums. Okay. And now, by the linearity of expectation, so we have plus 2 okay, and plus 4 xi square xj xk. Okay, and plus 4 summation xi xj xk and xl. Okay, so this is linearity of the expectation here. Okay, now because I and j are different, so xi square is the independent of xj square. Okay, so they are, because xi and xj are independent, and the square of xi is a function of xi. Square of xj is a function of xj. Alright, so these 2 functions are independent, so that's because they are independent. So the expectation of their product become to be the product of their expectations. Okay, so we have this term. Now in here, we know xj and j and k are different. Okay, all right. So these 2, xi and xj, are independent. But how about the I? I may be different from j and k, but it is possible I equal to j or I equal to k, right? But if I equal to j, then I should be different from K. If I equal to K, then I is different from J. Right? So that it is possible that this is equal to alright, so if I, J, K are different, right? If they are different, or this is equal to alright, or this is equal to if I equal to J, if I equal to K. Right? So there you have this. Now, in here, we just know I and J are different. K and L are different. Okay? But it's possible that I equal to K, or I equal to L, or J equal to K, or J equal to L. So that there are quite a few possibilities, and right. So that the first case, if I, J, K, L are distinct. Okay? So if they are distinct, so maybe I use distinct. Okay. Now, or expectation that this is x I square, or I use so xj, xk, if I equal to K and J, K, L are distinct. Or if I equal to L and J, K, L are distinct. Okay. Okay, and if J equal to K and I, K, L are distinct. If J equal to L and I, K, L distinct. Or if I equal to K and J equal to L. Okay, so we have okay, so we have those cases here. Now, in this case, because xi has zero means, right? We assume xi has zero means, so that this is zero, because this is zero, this is zero. Okay, this one may not be zero, but this is 0, 0, and also this is 0, and so this is 0. Okay. Now for this case, this is 0, this is 0, this is 0, this is 0. Okay. And this is 0. But this one may not be 0, right? Because this is the second moment. Okay. So that we can see plus in here, so we have 2 . All right, so this is all right. Now, because any of these 3 cases is 0, so that this term disappeared. In here, the double sum, because that all these cases has 0 value except this case. But this case means that I equal to K and J equal to L. So that we have plus 4 summation okay, so we have this. All right, so now because x of I has identical distribution, so that we can use x1, right? X of 1 as a typical Raman variable. So this is the first moment of x1, and they are all identical, so we have n of them. Right, and here, right, so this is equal to, because this is equal to expectation of x1 square, this is also equal to, okay, all right, so how many, because this is a constant, and so we have 2 the square here. Now it's 4 times 2 and minus 1 square. Okay, so we cancel. This is 2. So now we have n, and the n times the first moment plus 3 times n minus 1, and the square of the second moment So we have that. Okay, now, since 0 is less than or equal to the variance of x1 square, right? So the variance of x1 square is equal to the second moment of x1 square. So this is x1 fourth power minus x1 square here. So which means that the first moment is bigger than or equal to the square of the second moment, right? So that the expectation of x in the fourth power, right, is upper bounded by, okay, so we can add them together. So this is become 2, 3n square minus 2n, and the first moment here. Well, so we have this one, and then if we divide this by the first power of n, okay, and so this is first power of n here. Okay, so if we divide them, then so we will see that this is less than or equal to, right? So the minus term, we can neglect it. So this is the 3 divided by n square, and the expectation of the first moment here. So this is the upper bound. All right, so that, and then the expectation of the summation divided by the first power of n. Okay, we know that this is, okay, because that all these random variables are non-negative. Okay, so we can exchange the order of expectation and the series sum. Okay. And this is finite, because 1 over n square has a series sum which is finite. Okay, so we know that the expectation of this summation is finite. Therefore, the probability that summation of, alright, so this is series sum, okay, is finite with probability 1. Otherwise, okay, so otherwise, so if there x, right? So otherwise, if the probability of summation is positive, suppose that then the expectation of this summation is equal to the expectation of the indicator that times the indicator that okay, because 1 is equal to this indicator plus this indicator. Okay, right, and so this will be greater than or equal to, okay, this okay, because this is sum, this expectation always non-negative. Okay, so this one. But this is equal to expectation of infinity plus indicator so that this is infinity times the probability of the event equal to infinity, all right? And because this is positive, okay, so this is infinity, okay? So that the expectation must be infinity, and this is a contradiction. Okay? Here we have shown that this expectation must be finite. And this, so if this is true, right? So which means that this is equal to 1. Okay. Okay, and so that so we, all right. So let's omega 0 to be the event. Okay, then we know this event equal to 1, and for all omega in omega 0, we know that Okay? Finite. Okay. And so this is implies that if a serious sum of the first power is finite, so which means that this goes to 0 as n goes to infinity. So this is a necessary condition, right, in calculus. Right, so the terms must go to 0. Okay. So that, what is that? This means that it's n omega n, alright, so which is x1 omega plus x2 omega plus plus xn omega divided by n goes to 0 as n goes to infinity. Right? So which means that the sample mean goes to 0. Alright? With probability 1. Okay, so we prove the case that the mean is equal to 0. Mean equal to 0. Okay. Right. So now the reason why, because this proof is a simple proof, so why we need the first moment, central moment, is because that we want to have the first power of the sample mean. Right, of the sample mean has expectation less than or equal to 1 over n squared. Okay, so we need the n squared because that such that the summation, okay, is finite. Okay, it's finite. If the requirement is only that the second or the third central moment is finite, will be not enough. Okay, because that you will see that you can't have the n square because 1 over n, right? 1 over n has series sum which diverge to infinity. Okay, so this is the reason why we need the first power. Okay, and sort of the first central moment here. Okay. So that is the idea. Now the general case, basically we just show the theorem when mu equal to 0. Okay. Now, when mu is not equal to 0, we apply the preceding argument to the random variables x sub I minus mu to obtain that 1 over n summation I from 1 to n xi minus mu, the limit n goes to infinity is equal to 0 with probability 1. Okay, and so such that the limit n goes to infinity 1 over n summation I from 1 to n x sub I go to mu with probability 1. Any questions? Hi. Now we will state a theorem, right? So we will state the strong law of large numbers for a more general or more relaxed condition for just uncorrelated random variables. Okay, because the ordinary statement here the sequence of random variable must be IID, right? They must be independent and identically distributed with finite mean. Okay? Now, independence can be replaced by a much weaker condition, say uncorrelated. But one additional condition must be imposed. So let me see. All right, so x1, x2 will be a sequence of uncorrelated random variables, which means that the covariance of two different random variables must be 0 for all I not equal to j. Okay? So this is actually a very mild condition, right? Such that for some constant okay, for some constant n greater than 0, xi has finite secomponent and also bounded by m. Okay, right. So this condition is stronger than the condition that only have finite mean. Here, we require that each random variable except I has finite second moment, and this finite second moment has a common upper bound. Okay, so they have a upper bound here, but the independent identically distributed requirement is broken, right? So we don't need to have IID random variables. Okay, so independence is not required. We only is replaced by uncorrelated means. Okay. And the xi's can have different distribution. Okay, so they can have different distribution, but it requires that they must have finite second moment for each xi, and this finite second moment has a common upper bound m. Okay, so this condition about the mean, this is stronger than to have a common mean. Okay. Right? So this is the price you need to pay, but this is not severe. Okay? If in many practical systems that the second moment, because this is referred to the power of a signal. Okay? And we say that the power has upper bound. That is reasonable, right? Because in the practical system, you can't have a signal with infinite power, right? So that this is a very practical condition you can have. Then that the centralized sample mean here, right? So you add the deviation. Okay, this is the deviation from the mean, right? For each signal, all right? And you add all the deviation divided by n. And the limit as n goes to infinity, this is equal to 0 with probability 1. Okay? So, which means that there exists an event omega 0 in the sigma algebra F with probability 1 such that for each outcome in omega 0, the average deviation, right? So this is the average deviation, goes to 0 as n goes to infinity for all omega in omega 0. Okay, so this version is very useful. Okay, very useful in practice. Okay. And I give a remark. So for a proof, because this theory is quite general, so the proof is a bit involved. Okay, so for a proof, please see our theorem 5.1.2 in Kai Chung's again textbook, a course in probability theory. Okay. Okay, so you can see that. Okay, so you see up to now, we actually discussed 3 different concepts of convergence. All right, in the weak law of large numbers, in the central limit theorem, in the strong law of large numbers. All right, so I want to explicitly mention these 3 different concepts of convergence. Okay, so let's say the weak law and strong laws of large numbers, and the central limit theorem involve different mode of convergence. Okay. All right. So I would like to speak out these 3 different modes of convergence, and will discuss their relationship. Okay, so definition. Okay, 8.4.a, a sequence of random variables is said to converge to a random variable x with probability 1. So we say with probability 1, if there is an event omega 0 in the signal algebra with probability 1, such that the limit as n goes to infinity of xn omega is equal to x omega for all omega in omega 0. Okay. Okay, and so you can see the stronger or large number actually state that the sequence of IID random variable with finite mean, okay, has the sample average which converges to the constant random variable mean with probability 1. Okay, so the stronger or large number actually have a statement by using convergence with probability 1. Okay. All right, and there is a categorization about convergence with probability 1. So I state in proposition 8.4.a. So a sequence of random variables converges to a random variable x with probability 1 if and only if that the limit, if only if for any epsilon greater than 0, the limit of the probability that the difference, all right, the difference between xm and x is less than epsilon for all n greater than or equal to n. Okay, so that this is event, it's an intersection because for all, which means that this event must be satisfied for every n greater than or equal to n. Okay, and the probability of this event when n goes to infinity is equal to 1. Okay, and this is equivalent to here the limit of probability that xn minus x is greater than or equal to epsilon for some m greater than or equal to n. So this is OR. Okay, and when n goes to infinity, this is 0. Okay. So the proof, maybe I will give you, please see, lecture notes. So I will send you lecture notes. Okay. It's a little bit technical, so I think I'll just provide you a proof, right, in the lecture notes. Okay. So maybe I will see this event for all, right? So this is the intersection of m from n to infinity. That's okay. So it's the intersection of this event, and for some, this is the union from n to infinity. All right. So this. Right. So this is about the first concept of convergence. The second concept, definition B. A sequence of random variables is said to converge to a random variable x in probability, or in short, in PR, but if for any average value is 0, the probability that this either is greater than or equal to epsilon. Okay, so this event has limit equal to 0 as n goes to infinity. Okay, and if you refer to the weak law of large numbers, you will see the weak law of large numbers state that if we have an IID sequence, right, with finite mean, okay, then the sample mean will converge to the constant random variable mu in probability. Okay, in probability. So the weak law large number involves the concept of convergence in probability. Right. So now we have a proposition 8.41b. If a sequence of random variables converges to a random variables x with probability 1. Okay, so if we know that a sequence of random variable x sub n converges to a random variable x with probability 1, then this sequence converges to x in probability. So convergence with probability 1 implies convergence in probability. Okay? So if you have, for example, in this case. For this case, right, this sequence, okay, converge to 0 with probability 1. So this sequence converges to 0 in probability. So when we have a stronger large number, then it will imply the weak low large numbers. Okay. All right, so this answers, because last Tuesday, you have asked me, how about random variable xi with different distributions, right? And that is one of the version you can have it, right? Instead of the Khinchin's, because in Khinchin's version, we know that the weakest strong number for Khinchin's version is that we require pairwise independent, right? But identically distributed random variables in that case. And in this case, independence has been replaced by uncorrelated. Okay, so uncorrelated is weaker than pairwise independence, because pairwise independence implies uncorrelated. All right, so this is weaker than Khinchin's case. Okay, and in here, xi may have different distributions. Okay, but the price you pay is that xi must have finite second moment, and all of second moment is upper bounded by a common upper bound m. Okay, so in this case, then we have convergence with probability 1. And so this implies that this sequence of random variables will converge to 0 random variable in probability. Okay? Right. So this is the consequence of this proposition. Convergence with probability 1 is stronger than convergence in probability. Okay? Right. So here, so we have that. All right, and a proof. I will prepare a lecture notes. Please see the lecture notes. Okay. Right, so this is about now. Now we define the third convergence concept. So let f sub x, f sub x1, f sub x2, etc. be CDFs of random variable x, x sub 1, x sub 2, etc. respectively. Now the sequence x sub n and the sequence of random variables is said to converge to the random variable x in distribution. Shortly in dist. Okay. If the CDF of x sub n at the point x converge to the CDF of number x at the same x as n goes to infinity. Okay, this one for each x in R at which the CDF of random variable x is continuous. Okay. All right. So this is called converge in distribution because we just require the convergence in terms of the cumulative distribution functions. Okay. So for every x at which this function, the CDF, is continuous. Yeah, if for x at which f of x is not continuous, then we don't care. What we care is all the point x at which f of x, the CDF of an variable x, is continuous. Then for fixed such x, then the sequence of these numbers, right, goes to this number. Okay, so this is called convergence in distribution. Okay. Now, superposition 8.4.c. Right, so if a sequence x sub n from 1 to infinity of random variables converges to a random variable x in probability, then it converges to x in distribution. In distribution. So convergence in distribution is weaker than convergence in probability, and then convergence in probability weaker than convergence with probability 1. All right, so the strongest is the convergence with probability 1, and the weaker one is convergence in probability. And then the most weakest one is the convergence in distribution. Okay. Okay, so again, please see the lecture notes. Okay. So, any questions about these three concepts of convergence? So, the statement of central limit theorem is the concept of convergence in distribution. Okay, and as we know that the convergent distribution, which is a normal distribution, and we know the CDF of a normal random variable is continuous. Okay, so you have to check all x in R. Okay. Any questions? Okay. And in the future, you may encounter the fourth convergence concept in probability theory. For example, you may encounter convergence in mean square. Okay, in mean square. But I don't have enough time, so I will not mention this concept. Okay? All right. So, and the convergence in mean square is also a very good concept in engineering. Okay? But I think the instructions of any course related to convergence in mean square, or in general convergence in the piece means, will give you a precise definition. But at that time, you may refer back to here, all right, to review the three concepts, okay, we have discussed in today's lecture. All right, so we have some other inequalities to derive. Okay. And these inequalities is used to estimate some interesting events, to estimate the probability of some interesting events in engineering and science. Okay. All right, so the first one, we will cover one-sided shape-shift inequality. We encounter two-sided shape-shift inequality in a previous section. Okay, so if x is a random variable with mean 0 and finite variance sigma square, then right, so that x has 0 mean by the finite variance, then for any a greater than 0, the one side, so this is why this is called one-sided. Right? So this is the right-hand tail, right? The right-hand tail. So this right-hand tail event has probability upper bounded by the variance of random variable x divided by the variance plus a squared. All right, so proof. All right, so we let b be a positive number. Then we have here probability that x greater than a is equal to, if we add the same number b, okay, on both sides, and because, okay, here, then, and then we take the square, okay, so we take the square here. And why we have upper bound? Because that this event actually is the union of two events, right? This event is that x plus b greater than or equal to a plus b this event, disjoint union of x plus b less than minus a plus b. Okay? So it's bigger than this one, right? It's bigger. Oh, including it here. Sorry about, I forget to put equality sign. All right, so these two are disjoint events. Why? Because A plus B is positive, right? B is positive. A is positive, so A plus B is positive. Okay? Right? So that this is bigger. Now the random variable y we define to be x, the square of x plus b. Alright, is non-negative. And we know we can compute, before we can apply Markov inequality, we compute the expectation of y. So the expectation of y is equal to, so this is expectation of x squared plus 2b times expectation of x plus b squared. And so that now because x has zero mean, so that the central term is 0. Okay, so we have the variance, and also the second moment is equal to the variance of x and the b square. So this is sigma square plus b square here. Okay, now by Markov, now so we can apply Markov inequality. So by Markov inequality, we know that, right? So this tail probability, as we already shown here, is probability that y greater than or equal to a plus b square here. Right? And so this is a plus b square and the expectation of y. And here is square. Oh, I forgot to indicate that this is finite. Okay, and a square of a plus b for all b greater than 0. Okay, and so this probability upper bounded by this ratio for any b greater than 0. Okay, so we have a lot of upper bound, so we find a minimum upper bound, right? Okay. Now, so the upper bound as a function of b square, as a function of b for positive b, so this is minimized when b is equal to sigma squared divided by A. So that, okay, this is a differentiable function, okay, of B. So you can use the calculus to find the minimum value there. So the minimum value is this number. So that's the probability of x going equal to A is less than or equal to. So you can do it x sigma square plus divided by A. And A plus okay, and we can see after the computation, you will see this is sigma square plus A square. Okay, so this will be the best upper bound, which is the minimum upper bound. Okay. In terms of this, okay. Okay, so we obtain another. So this usually you can compare usually this upper bound in many situations that give us a very good bound there. Okay, and corollary. No, because the statement of one-sided Chebyshev inequality here required whenever x has zero mean. But how about if we have a general mean mu? Okay, so here is a corollary. All right. Again, this is also the one-sided Chebyshev's inequality. Okay, so if x is a random variable with mean mu and finite variance sigma square, then for any A greater than 0, okay, the right side mu plus A, okay, right? So the right tail event here has probability upper bounded by sigma square and sigma square plus A square. And how about the left? Mu minus A here. So the left tail event also have the same upper bound. Okay? So it gives us that is true. Okay, so the proof is here. Okay, so we, by applying proposition 8.5.1, okay, to y equal to x minus mu, and z defined to be mu minus x respectively. So we have, so here, so we know that y has zero mean, and variance of y is equal to variance of x, which is sigma square, okay? And also, expectation of z is equal to 0, of course, right? Because it's mu minus x. And the variance of z is equal to variance of x is equal to square. So they have the same. Right, so the requirement for the one-sided chip-shift inequality with zero mean and the final variance is sigma square. Okay. All right, so we have y greater than a equal to, this is, okay, and the probability of z greater than a squared, right? But what is that? This is x, okay? And so that x greater than mu plus a here. And this is mu minus x greater than equal to a. So that x will move this way, is this thing equal to mu minus a. Okay, you move x to the right hand side and a to the left hand side. So it's mu minus a, that's greater than equal to x here. So you have that. Okay, and you have that. So this corollary actually is a direct application of this proposition here. Next is also a very useful bound, which has been used in communication system. Okay, channel bounds here. Let x be a random variable with moment generating function m sub x of t, which is defined on a neighborhood of the origin in the real line. Okay, so the total bound require random variable x has moment generating function, okay, on the neighborhood of the origin, which means that this random variable has mth moment of any order, right, or for any m. Okay. Then, for any A in R, okay, so A can be positive or negative. The probability of the right tail, okay, can be upper bounded by take the increment for all t, which is positive, such that m over xt is defined. Okay. We know the momentum function is defined on the neighborhood of 0, right? So it's defined for t greater than 0, but maybe less than some epsilon. Okay, so you just find for all t such this is defined, then you find e minus ta and mxt. Okay, so you find the increment of this function. Okay, and for the left tail, okay, now the increment you take also would be t, which t is negative, and is defined for e minus ta m xt. Okay, another proof. Now, for any t greater than or equal to 0, where m of xt is defined, we have that p x greater than or equal to a, and because t is positive, so that if we multiply t on both sides, the direction of inequality does not change. Right? So, and now we use the exponential function, and because exponential function is a monotone function, so that we have ETA here. Okay, so these events, they are all the same. And because this is a non-negative random variables, and this is the positive number, so by using the Markov inequality, so we have, okay, so this is Markov inequality. Markov inequality. All right, and so this is E minus TA, and this is the moment general function here. Okay, so this probability upper bounded by this one, and so when we take the increment, then you get the base upper bound. Okay, and for any t which is negative, okay, where the moment general function is defined. So we have that p x less than or equal to a. Okay, when we multiply a negative number, we have to change. So we have to change the direction of inequality because t is negative. All right, and again, exponential function is monotone. Okay, so we have by the Markov inequality, again. And again, take the increment. Okay. All right, so Chernoff-Bound, you can see the idea is similar to the idea for the one-sided chip-chip inequality. Okay, using some parameters. Okay, but for Chernoff-Bound, we require the moment unit function is defined on a neighborhood of the origin in the real line. Okay, so that, and with a stronger condition, usually this bound is better than the one-sided chip-chip inequality. Okay, right? But it's more involved because that you have to find the increment of this function. Okay, and so you should know what is this moment unit function to have. Okay. Any questions about Chernoff bounds? We mentioned Jensen's inequality for conditional expectation before. Okay. Now, there is a version of Jensen's inequality for general random variables. Okay. So we recall and Jensen inequality involving convex functions. Okay, so we introduced convex function before. A real valued function f of x on an interval I of the real line is called convex if lambda x1 plus 1 minus lambda x2 is less than. So the function value of this convex combination of x1 and x2 is less than u2 lambda 1, lambda f of x1 plus 1 minus lambda f of x2. For all x1, x2 in the interval, and for all lambda in between 0 and 1, including 0 and 1. Okay, so we have a typical is here. Okay, so this is convex. Okay. F of x is called strictly convex if for x1 not equal to x2, equality holds if and only if lambda equal to 0 or lambda equal to 1. Okay? Because if lambda equals to 0, then this is f of x2. Okay? Equal to f of x2, of course. Okay? Otherwise, if lambda is greater than 0 but less than 1, then this is strict inequality, not equality, okay? So this is called strict convex. Right? Now, by the mean value theorem for differentiation. Okay, so I believe you have learned mean value theorem for differentiation in calculus. A real valued differentiable function f is convex on an open interval AB if and only if we have xt, right, has this order relation, right, implies that f prime of x is less than or equal to f prime of t. Okay. i.e., the derivative f prime is a monotone increasing function on AB. Okay. Okay. So if the real value function f is differentiable, okay, in an open interval, then it is convex if and only if its derivative is a monotone increasing function. Okay, so for this example, you see that the slope, you can see the slope become bigger and bigger, right? So this is negative, go to 0 and go up to positive. Okay, so you can see the slope, right? The slope is a monotone increasing function. Okay. But in general, as I have indicated before, that so I state that proposition 8.5.a, if f is convex on an open interval AB, then f is continuous on AB. Okay. Okay, so we can make a remark is a random variable taking value in an interval which may not be open, okay? I of the real line, and f is convex on I, then f is piecewise continuous on I, and then f of x is a random variable. Okay. Why we just know that f is piecewise continuous is because that the interval I may not be open. If I is open by this proposition, f is continuous, no problem. But if the I is not open, so for example, you may have, so this is A, this is B here. So you may have the okay, you may have jump at the two end point, but this function again is also convex, which is convex on AB, right? But it's not continuous. Okay, so you can see this is of course this is because the chord you can see always up, right? The chord here. So this is a convex function on closed interval, but it's not continuous on this closed interval. But if you look at a subset, the open interval from A to B, right? Then it's continuous, as being stated in this proposition. And so you can see this function is piecewise continuous. Right? We defined piecewise continuous function before. And any piecewise continuous function is Borel measurable. Okay? Borel measurable. So f is Borel measurable. So f is piecewise continuous, implies that f is Borel measurable on I. Okay, so that's f of x is a random variable. Okay, so we use f as a data processing function, and because f is Borel measurable, so f of x is a random variable, of course. Okay. Any questions? So this is first point. We marks the second point is that if x is a random variable taking value in an interval I of the real line, and has a finite expectation E sub E of x, then this expectation is also in I. Okay. Indeed, in section 7.1, right, in chapter 7, we have shown that if X is bounded by A and B, okay, with probability 1, right here, then we show that okay, then the expectation is also bounded by the same endpoint A and B there. Okay. But this is always true for any interval I. Okay, this interval I can be infinite interval. Okay, semi-infinite, or finite interval with endpoint or without endpoint. Okay, so this is always true. Okay, even though in section 7.1 we prove just one of the case, right? But this is true. And the proof will be similar. Now we will state Jensen's inequality. So let X be a random variable taking value in an interval I of the real line and have a finite expectation E of X. Okay. Now let F be a convex function on I, and as we know, F is Borel measurable. So that this is a random variable, and this random variable have a finite expectation too. Okay. Then the function value at the mean of random variable X is less than or equal to the expectation of the f of X. Okay. Okay, so this is the Jensen's inequality. And moreover, if F is strictly convex, then the equality in above, so the equality in above holds if and only if x is equal to a constant with probability 1. Which means that x is just equal to its expectation with probability 1. i.e. x is a constant with probability 1. Okay, so this is the Jensen's inequality. Okay, so and there are a lot of applications. For example, examples that there are many applications. F of x is s squared, is convex on R. Okay, so the square function is convex on R. Okay, so if x has a finite second moment, then we know that f of ex, so the square of this is f of ex is less than or equal to expectation of x. Okay, and this is of course true, right? The square of the expectation is less than or equal to the second moment. Why? Why? Because the difference is just the variance. Okay, so that is the second. F of x is equal to the natural logarithm of x, okay, is convex. The positive axis here. Oh, minus, I'm sorry. Minus, this is 1 here. Okay, so you can see the minus logarithm of x is convex here. Okay. Okay, so if we note that the logarithm of expectation of x here, okay, is less than or equal to the expectation of natural logarithm x here. Okay, so if x and if x is greater than 0 and x have finite expectation. Okay, so if x is positive and x must have finite expectations, then so we have this inequality here. Okay, so we find a low bound for this expectation. Okay. So this is Jensen's inequality. Okay, the textbook for a proof of the Jensen's inequality. When f is twice when the convex function f is twice differentiable, okay, please see the textbook. So textbook give proof under a stronger condition that the convex function f is twice differentiable. Okay, so that it gives us this inequality. Okay, but for strict convexity, that the equality holds if and only if that is a constant with probability 1. It's a little bit complicated, okay? So that it can be proof for the general case. Okay. So I will see that if you see it is possible to give you a proof, okay, in lecture notes. So this is the Jensen inequality. Okay. Now we have a last useful inequality. It's about increasing function. So any real valued monotone increasing or decreasing function on R is barrier measurable. Okay. In particular, any CDF is barrier measurable. Okay, so that is interesting to have. All right, so that, and okay, so let X be a real valued random variable on a probabilistic model omega f p omega 0, okay, with a CDF f of x. Right? So suppose x is a real value random variable on a probabilistic model with the CDF. It may not be possible to have a random variable y on the same probabilistic model such that y has the same CDF of x and is independent of x. Okay. So if somebody tells you that, okay, given suppose x is the random variable, and that y is another random variable, has the same distribution as x, and is independent of x, then this statement may be false, because that it may not be possible to find such a random variable. Okay, so that so you should be because time limitations. So I will give you a common example in the lecture notes. Okay, so that is important, but we can. This is the negative part. This is the negative part, but we can construct not only two, but an infinite sequence of independent and identically distributed random variables with the same CDF f of x as x. Okay? And which are defined on another probabilistic model x. We use x0, that's f and p. Other than okay. So, but if we not insist to construct random variable on the same probabilistic model, then we can consider other probabilistic model. So we always can do so. Okay. And actually we can construct an infinite sequence of RID random variables. And the distribution of each xn is the same as the distribution of x. Okay? Distributions. So, you may have random variables defined on different sample space, different probabilistic model, but have the same distribution. Okay? So the construction always possible. Okay, so we can do the construction. Okay, and I will give you a construction in the lecture notes. Okay, how can we do that? Okay, on another probabilistic model. Okay, so if So we will use this concept in the last inequality. Okay, so let f and g be two monotone increasing. Okay, so monotone increasing functions on the real line, and x is a random variable such that f of x and g of x, because f and g are monotone, so they are measurable. So f of x and g of x are random variables, right? And these two random variables have finite second moment. Then the expectation of the product of these two functions of x is a lower bound of the product of the expectation of f of x and the expectation of g of x. Okay. Okay. So this bounds is quite useful in many situations here. All right, and so now the proof given in the textbook is not correct actually, because it says that it says first that let y is a random variable which is independent of x and has the same distribution as x. This statement is incorrect because, as I indicate, that there is a counterexample. Okay, so here the beginning here is that we will say let x1 and x2 be two independent and identically distributed random variables having the same CDF as x. And as we know from our previous discussion, x1 and x2 may be defined on different probabilistic model from that where x is defined. Okay. Right, so you should use x1 and x2, right, which may be defined on a different probabilistic model. But x1 and x2 are independent, but they have the same distribution as x, so they have the same CDF as x, okay? And then proceed. And the following argument, and they will also proceed the same arguments as that in the textbook. Okay, so I stop here. Okay. So the rest of the arguments in the textbook will be correct. If you use, instead of use x and y, you should use x1 and x2. Okay. All right, and then you proceed the same arguments as that in the textbook. It give you that. Okay. So that is the last the inequality we have in this chapter. All right. So there are some material I have to prepare for you in your lecture notes. Okay. So any questions? Well, so no questions. That's good. So this is the end of class lecture in this semester. And so next Thursday we will have one examination. Okay. But remember, next Monday we have the final quiz examination, the number 14, and we will have no class lecture next Tuesday. All right. So you will have gap time to prepare for the final examination. Good luck. All right.